Hello everyone and welcome back to my channel. In today's video, we are going to look at something very interesting in physics. Things that we cannot actually see, but whose effects we can clearly observe. Now, when you look at the cup of tea, you can see the cup of tea is on the table and everything appears completely normal. The cup of tea or coffee is not moving at all. The table is not moving. There seems to be nothing interesting happening. But actually, there are several forces acting on that cup of tea. So, in this lesson, we are going to uncover some invisible forces. That's why I write here seeing the invisible. So most of people don't might see that this is a normal situation, but as you are a science student and in the science you are like physics student, so you have to consider which forces are acting on that cup of tea and on the table. So let's begin now, and we will also discuss the force, friction, drag, terminal velocity, buoyancy, free body diagrams, momentum, and conservation of momentum as well, collisions and impulse. So let's starting with this the case of the resting book. So as I discussed earlier, we have considered a cup of tea or coffee on the table. That's the same scenario we have discussed in the book resting on the table. So let's find out what is the actually happening this stationary book. So your first question is why doesn't the book fall through the table? Okay, the book is over here, and why it is not falling through this table? So we know the gravity is always there. So book is on the earth. So G, or you can say acceleration due to gravity, which is always there, and which is the 9.81 meter per second square. So the book is at rest. That means that some of the force is repel this force, and it is force due to gravity, and we will call it by a weight. Okay, and weight is given by m into g. Okay, and this weight is also a force which is exerting on the book in vertically downward direction. Okay, so if the book at rest, that means we know the what is the Newton first law says. If book is at rest, that means some force exerting on the book which is opposite to the gravity, oppose the gravity force. Okay, so here we call it normal contact force, which is applied by this table to this book. And the magnitude, as I told you, the magnitude of this force is two must be same. If they are not, the book is going to move. If they are same, their magnitude is same, the book is going to be at rest. But when you talk about the direction of these two forces are opposite. As you can see here, the normal contact force is in the direction of upward, and the weight it is in downward direction. Okay, so the gravity constantly pulling this book. downward at 9.81 meter per second square. Okay, so our question is why isn't it crashing through this table? Answer: the reason behind it is because the book is at rest. The vector sum of the all forces must be zero, according to Newton's first law, which is also known as the inertia law. The table pushes back with the normal contact force R. It actually perpendicular to the plane of the contact, perfectly balance the weight as we illustrate here. Okay, I hope you can get the point why book is at the rest because the external forces on the book is zero. Vector sum is zero because the force is vector quantity. That's why you have to consider the direction as well. I hope you get my point. But now, question comes in your mind that is it the Newton's third law applicable here, or you can say this normal contact force and the weight of the book. These are the forces, okay, and these are the pairs of the third law of Newton, which we have discussed earlier. Okay, so is it actually the pair of these forces? So let's understand. Many you are thinking that the weight and this R, normal contact force, they are the pair of the action and reaction force, which we have discussed in our Newton's third law. But you are thinking the wrong way. You have to recall the what is the third law. In third law, we have a take the condition. What is the condition over here? The condition is the action and reaction forces on different bodies. Here, in this case, you are seeing that normal contact force and the weight force, both forces acting on the book. There is no other body. We have considered the book experiences normal force as well as the weight of the book. So we have considered only one body over here. That's why you cannot say it is the weight and the R is the pair of the third law because in order to we have to speak, we have to consider two bodies and these two forces. One is forcing on the book and the another one is on the table in this case or on the other body. So I hope you get my point. Why we cannot say W and R or weight or the normal force are to be a pair of the Newton's third law. So again, you have a question because you are a curious student. So is in this scenario or in this case, is there any third law pair exist or not? And one more thing that I have to add is if the force is acting on one particular body and the body is at rest, that means it is kind of equilibrium position. So in this case, you can say the book is in equilibrium state because the total external forces acting on it will be zero. Vector sum is zero. So our question is the third law pair exists in this case? So let's find out. Here I understand understood that the what is a trap over here. So many students they are say that this is the pair, but this is not. So as I illustrate over here. I write here the both forces acting on the same body and they cancel each other and the book is going to be equilibrium. This is the Newton's first law. And then for the third law, must the pair or the forces pair must acting on the different bodies. Okay, one force is acting on the A body or another force is acting on the B body. So I hope you get this difference, clear difference of Newton's first law and Newton's third law. Now, our question is that is there any possibility of it have a Newton's third law pair or not? So yes, the answer of your question is yes. It is always there. So let us try to understand. We have a two pairs of Newton's third law. So for first pair, consider the scenario like if book is lying on the table and the book is exerts some force is on the table, which is R prime, you can say R prime, and at the same time, at the same moment, the table is also pushing the book in the upward direction, and which is called R. And the R and R dash should be equal. Otherwise, book is going to be in moving position. Okay, and here I'm right. The table pushes book upward direction. This is the R direction, and at the same time, at the same moment, not the back and forth. At the same moment, okay, the book pushes the table down, which means this R prime, and it should be equal to R is equal to I prime. Okay, it is a, in this case you can say that R and R prime forces are the pair of the third law. Okay, consider the second situation where the gravity is considered due to gravity on the earth pulls book down, means vertically downward position, means you can say W. At the same time, book also pushes the earth up. Let's suppose here you can say R, and it should be W is equals to R. But some students might get confused because Earth is stationary. We can say Earth is not moving at all. So your answer is somewhat right, but one more thing I have to add is Earth is moving upward. I hope you get my point, but it is a so small distance. We cannot experience it at all. Okay, because the mass of the Earth is very tremendous high. Okay, and the weight of the book is very low. That's why we cannot experience it at all. But it is always there. Okay, so I hope you clear your mind. So there are two scenarios in which we are going to discuss. We discussed that the two pairs of the third law, which one is R and R prime, and the another one is W and you can say books pulls author. Okay, so these are the main difference when you consider this resting book scenario. So I hope it's clear. We have discussed the friction earlier. Now we have discussed in detail. In this part, let's suppose a book is lying on the table. Now, if you pull this book in this direction, as I shown here, and at the same time, the friction is coming to the picture. Okay, so in this case, we have two scenarios. If our pulling force is equal to the friction force, or our pulling force is far more better and the friction is going to this direction, which is repels the relative motion of that body. So consider the first case in which we have applied force or pulling force is far more greater than this friction force. So there should be no equilibrium over here because these two forces are on the opposite direction, but one force is more than the other force. That's why the external force on this body, or in this case, the book, is not zero. The book is going to be moved in the direction of pulling. So book is going to this direction, is come into the motion. Now, if we know the any body is first at rest and it is going to the move, it needs some acceleration because the force, the external force, is not zero. So F is not zero, and we know the formula of M and A. If F is not zero, M is not zero at all. That's why we have a value, non-zero value of A. That means the body is going to be accelerated, means acceleration. The result is going to be acceleration. The book, first book is at rest, then it is going to move. Now, consider the second case in which we have taken the pulling force and the frictional force is going to be same. Okay. In this case, we have say that the book is in an equilibrium state. So we know in equilibrium state, the force, external force on any body is zero. Then we know the equation is F is equal to ma. If F is zero, this is m into a. M is not always zero, so you have to just do like this. In this, you can say A is zero. But some students say A is zero, that means the book is at rest or rest. No, this is not like that. If A is zero, that doesn't mean that V is zero. We should be in constant. Say if book is going some initial velocity, let's suppose V1, so it remains the same velocity or speed after the taking the force. Means constant velocity, either constant velocity or at rest. Here, the main thing is zero acceleration, means force is going to be a zero. Okay, I hope you got my point. The two cases of if pulling force is greater than frictional force, and if they are both same, then what will happen? Now we move forward. Here's one thing, that is the friction doesn't only occur between the solid objects. So what happens when object is moves through liquid or gas? So let's understand what is going on here. So when the object moves through the fluid, by fluid, which means a liquid or gas, okay, it experiences some resistance, and this resistance is called drag, drag or viscosity. Here, viscosity and drag. So as we discussed, the friction is always between the two solid surfaces. But if you want to go for a see that what is going on in the some mass of object is going through the some in water body or in gas state. So the same thing as we discussed in friction, we have a other name which is viscosity come into the picture. So let's suppose if you have air, okay, the next, let's suppose the particle or mass is going through this direction, and we have air medium, okay. So the particle is going through some speed, some sort of speed. So if the speed is low, the value of drag will be negligible. You can say drag is very proportional to the v. If velocity of the particle which moves into the air is going to be high, the drag will be high. So that's why I hear negligible at the low speeds and but crucial at the high speeds. Okay. In the second case, we have a water. Let's suppose we have a water liquid here. There's some particle or some mass of particle is going through this water. So what is happening over here? If you consider the liquid state, the viscosity come into picture. But if you deal with air or some kind of gas, it is a drag. It's not a drag, but they're doing it the same thing. Okay, repel the motion of this object. That's it. So if this particle is going through this direction, some kind of viscosity of this liquid in water, glue, kerosene, like that. Low viscosity means moderate drag force. What does it mean? If you compare water and glue, let's suppose water and glue, we know the water has low viscous liquid and the glue is high viscous than the water. So if you put the same mass of the body, which have a same mass, initial speed is v same, then you will notice that the particle of this particle 1, or let's say particle 2, particle 1 is going to be very speed in this table. Let's suppose it may take some time t1, and the particle 2 took some time to reach here. Let's suppose time t2. Here we'll notice that t1 is always less than t2. You'll notice that. So why? Our body of mass m, the same mass, same velocity, but the medium is different. Here you can say this is a glue and this is the water. But the glue has more viscosity than the water, that means more drag force, more repel to this motion. Okay, that's why the velocity of this particle of mass m and v velocity having the slow speed than this particle one. Okay, I hope you understand that what is the viscosity, viscous medium, and drag. What happens? The particle is going through some gaseous medium or the liquid medium. Now we all know the concept of, let's suppose F is equal to 0, then A should be 0. Okay, we apply this concept in this topic. So what anatomy of fall? So let's suppose an object is falling through the fluid, doesn't accelerate forever. It eventually hits the speed limit, terminal velocity. Let's suppose some particle, let's suppose having m mass and the v velocity. First of all, it's going through this liquid. Okay, you know, mg means weight or gravity is always there to affect this particle. Okay, it's kind of free fall situation. Let's suppose divide in three phases. First, the person here, you can see person is skydiving. Okay, doing some skydiving. First of all, he has some only the force downward, which is we called as a weight due to the earth. Okay, the earth gravity. So initial speed is 0. Let's suppose it's 2k is very low. And we have seen that drag is should be low when the v is low, velocity is low. The resultant force is just weight, okay, due to the acceleration of the earth. Now coming to the second phase, the resistance grows as the person is going this direction. We know g is always there. What is g? G is acceleration. It is goes affecting the velocity. Here a is accelerating, not deaccelerating. So v is going to be going to high at the time increases. Let's suppose v first 1, 2, 4, 9. It is going high direction, high values. Okay, attain some high values. So as v increases, the drag is always increases. Okay, as I mentioned earlier, here the speed increases, so drag increases. So one more thing is that drag is going affecting this person is upward direction, but the weight due to the earth is going this direction. Okay, the direction of these two forces are different. That's why we can say at some point where drag and the weight is going to be same. Okay, at the same time, the force at the same moment the force is going to be zero. We know the total external force is zero. Then the particle or this person is going to be at rest or either rest or constant velocity. Okay, so at that time the person or the particle is going through the this medium, as we discussed earlier, is going to be a some kind of velocity. It's called the terminal velocity, which is constant throughout the motion after this condition meet. Okay, so drag perfectly equals the weight. The resultant force is zero. That means acceleration is zero. That means constant uniform velocity. I hope you clear this concept, the terminal velocity. Now, in the we have discussed the viscous medium always there. If particle is going through this viscous medium, we have to consider one more factor, which is called upthrust, or you can say a buoyancy force. Okay, so if you want to do some forces, what is force acting on it? So let's draw it. Particle over here having a mass m. First force is going to be this direction, which is called mg. The another force is going to be this. You can say a viscous due to viscous medium. The different, if you take a different liquid, it may have some different viscous properties. Okay, but the biosip, the property of which the body is having some upthrust in this direction, upward direction. I hope you know the Archimedes principle. Okay, in Archimedes principle, they say the let's suppose this is a particle of having a mass v. If this particle replace this the same amount of water, and it will the same force it will experience on the upward direction, and it's called the buoyancy. Okay, so if you compare these forces downwards and upwards, the weight is on the downward side, and upthrust or buoyancy force and the viscous force is on the upward direction. Once you will get this condition, the particle is going to be some kind of terminal velocity in this liquid. Okay, so this is all about the equations that we need to understand so that we can get clear idea of which forces are acting on this body and how we can control over it. In our next video, we are going to see and we are going to learn how we draw, how we convert these physical forces into our mathematical tool. In order to solve the question related to this, what is the resultant force on the any body, or what is the acceleration of this body, and if more than one force is acting on the same body, you have to just resolve the some vectors that we will discuss in our next video. So keep practicing, keep learning. Thank you for watching. Subscribe for more physics lectures.